Determine if the table is linear or exponential. No problem, we did this last time. So I'm going to set up some fractions here, and we'll see if we have a linear situation. We'll compare changes in y's to x's as a fraction, and then we'll see if they're equivalent. So my change in y we'll start with. We got from 4 to 10. So if I was going from 4 to 10, I would do 10 minus 4, and that tells me that this went up 6. So that's my numerator. And then my denominator is the change in x from 0 to 1 is just to the right 1. So that's a 6-to-1 ratio. And if it's linear, then all of these will have a 6-to-1 ratio, even if it needs to be simplified. So right here from 10 to 25, again, I would find that by doing 25 minus 10. And that tells us it went up 15. So that's my numerator. And then my denominator, the change in x from 1 to 2 goes to the right 1. So that is a 15-to-1 ratio. And you could put that in the calculator, but anything divided by 1 is itself. So 6 is definitely not the same as 15. So these are not the same. And the reason that's important is because since they're not the same, this one's not linear. So having only two options, that tells us that this one is exponential. And since it is exponential, let's see what is happening to the values as we go down the table. So remember, if I wanted to find out what's being multiplied, then I would take, just take the second box here, which is 10, and then divide it by the first one, 4. And then I can see that my factor here is 2.5, which means that if you were to take 4 times 2.5, you'd get 10. And if you did 10 times 2.5, you'd get 25. If you did 25 times 2.5, you'd get 62.5. And you could continue this down, but this is just to show that we can find what is being repeatedly multiplied. And since it's being repeatedly multiplied, that is what makes it exponential. So we got 3 objectives today. I can write basic exponential equations. I can calculate basic exponential situations. And I know the difference between linear and exponential relationships, which is what we saw last time. But today we're going to be seeing this more in word problems. So take 30 seconds, copy this down, then we'll get started. So we've seen this slide already. Just to remember what an exponent is, we're going to be talking about bases and exponents. In this situation here, the 5 is the base, and the base tells us the number that's being repeatedly multiplied. The exponent here in this case is 4, which tells us how many times it's repeatedly multiplied. And if we were to see this on paper, we should be able to read it as well. But this would read 5 to the power 4, which is showing right here as well. Okay, so when we see something like this, we need to be able to read it. And so if we saw something like this as well, something like, I don't know, 8 times 7 to the power of x, we need to know what this means. Okay, 8 times 7 to the power of x. By the way, if it comes in this format, which we're going to be seeing today, the 7 is to the power of x. The 8 has a power, but it's 1. So these do not both have, these two factors don't have an exponent of x. The 8 has an exponent of 1, 7 to the power of x. So it's important not to get that confused. And again, we've seen this one before. So 6 to the power 4, that's how this one reads. If we wanted to rewrite this with repeated multiplication, we could. Again, the base is 6, the exponent is 4. So we have 1, 2, 3, 4 6s all being repeatedly multiplied. Or if you start with repeated multiplication like this one, 7 times 7 times 7 times 7 times 7, you get 7, a base of 7, to the power of 5. So again, the base just tells us what number is being repeatedly multiplied. The exponent tells us how many times it's being repeatedly multiplied. Now going back, when we were writing equations for straight lines, you needed 2 things. You needed the slope and you needed the y-intercept. Unless you were writing it in a direct format, which was the ax plus by equals c. But this stuff may be mixed in a little bit with some of the assignments. So you have to keep that in mind. If you're not looking at an exponential situation, which means that it's not showing repeated multiplication, maybe it's just adding a specific amount every time, then it becomes a linear situation, which then we can find in slope-intercept form. Yeah, exponential equations are going to be, they're going to look very different because you're doing repeated multiplication. Division we'll usually show with fractions, just multiplying by fractions, but you could divide if you wanted to. So our exponential equations are going to look something like this. And it's important to know what you're going to start with, especially in these word problems. So we're looking for starting values again, or initial values, or you could call it a y-intercept. It means the same thing, but we're not looking at graphs. But once you know what you're starting with, that's this value right here. So you take the value you start with, and then if they say something like, well, it's going to double every time, well, you know that you're multiplying by 2 over and over and over. So you could take that starting value, multiply it by 2 in that case, and then the exponent tells you how many times you repeatedly multiply that by whatever it is. It could be 2, it could be 3, it could be 5. Doesn't matter. So yeah, again, the exponent just tells us how many times it's being repeatedly multiplied. Now there's some terms we're gonna have to understand. If we see the word double, that tells us that we're gonna multiply by 2. I'm putting these out there just in case you're not familiar with them. But triple, which I may have spelled incorrect, but that'd be multiplying by 3. And then, yeah, they may even put in there quadruple. I don't remember that they go any further than that. And again, I may have spelled that incorrect, but that quadruple is multiplied by 4 repeatedly. Okay, so they may say something like, well, you start with this amount and then you triple it every year for 5 years. Okay, so you're tripling it, so you'll be multiplying by 3, but every year for 5 years means that you do this 5 times. Okay, so this creates a basic exponential equation for us. So for this one, we got a rabbit population, and it said you're going to start with 12 rabbits, and after that it's going to double 5 times. So double means that we're going to multiply by 2. Okay, so multiplying by 2 5 times. Now we could write the exponential equation for this one, and we know it's exponential because it's repeatedly being multiplied by 2. So again, this is just another way that we can know that we're dealing with something that is exponential. Okay, so what would we do here is we would take the starting value 12, and it says it's going to double 5 times, right? So double means multiply by 2. So if I did this once, I'd take 12 times 2, and I'd say, well, after you double those 12 rabbits, you'd get 24 rabbits. But we're going to do this 5 times, so we're going to double it again. 24 times 2, boom, 48. And if I double that, 48 times 2, 96. Now I've doubled that 3 times. I'm going to double it a 4th time as well. So I got 96 times 2, and that gives me, I'm just putting this in the calculator, by the way. That means after doubling 4 times, you have 192 rabbits. But I got to do it 5 times, right? So I'm going to double this again, and I end up with 384 rabbits. Well, that's nice. It's just that it didn't ask for us to actually figure out how many rabbits would be there after doubling the population of 12 5 times. The reason I did this is because you will on the assignment. Okay, it's one of our objectives. So could you do this? You could. But it's asking for an expression that would show a rabbit population starting at 12 rabbits. Okay, so if I wanted the expression for this, I'd say, look, what we did here is we took the 12, right, starting here, and then I multiplied that by 2. Well, after that, I just kept multiplying by 2, didn't I? So I just said multiply by 2 times 2 times 2 times 2. We did it 5 times. So this would be the expression. If you put this in the calculator, you're going to get 384 rabbits. But we can actually simplify that into its exponential expression. So we started with 12. We multiply that by 2 because it was doubling every time. And then we had 1, 2, 3, 4, 5 of these. So we got 2 to the power 5. Again, if you were to put this in the calculator, you would get, again, 384 rabbits. But that's the expression that they're looking for on this one. But again, this takes on that format of a times base b, and that's why we're using b there, to the power of x. Okay, a is the value that you start with, and then b is the value. The base is the number you're repeatedly multiplying by. X is how many times you did it. So we started with 12 rabbits. We doubled it 5 times. That's what this expression right here is telling us. I usually like to show this with y equals, just to make it an equation, but they didn't want an equation, they wanted an expression, so I gotta keep it like this. Write an expression that would show an initial population of 245 endangered geese, quadrupling each year for 9 years. So first off, it says you got some kind of initial population here. Initial means that you're gonna start with this many, I guess, endangered geese. But then it says that that population, we're gonna quadruple it each year for 9 years, right? So quadruple means that right here, we're gonna multiply by 4. Quadruple, quad is 4. So multiply by 4 here. And we're gonna do this every year for, again, 9 years, all right? So I'm gonna do this by hand just to start with. So I'd say 245. If I were to quadruple that, so I'd multiply it by 4, that would be after 1 year. So 245 times 4 in my calculator. And this says that if I did that, I'd have 980 geese after 1 year. But then I'm going to multiply that by 4, right? Because that also will quadruple. I got to do this 9 times. And if I quadruple that many, then I'd have 3,920, which if we quadruple that, so quadruple that, I get 15,680. Okay, so we quadrupled it 3 times. Let's make it 4. So I'm going to quadruple the 15,680, and I get 62,720. So that's how many geese are in the flock, I guess, after, what is that, 4 years? Thank you. But I got to quadruple that value as well. So I'm going to quadruple, again, just putting in the calculator, 250,880 on this one. And I got to quadruple that one too. So what is that? This is our 6th time. So after 6 years, there would be 1,003,520 geese. Let's quadruple that. So this would be, what is this? Our 1, 2, 3, 4, 5, 7th year. And that gives me 4,014,080 geese. Right? And then I quadruple that again. Looks like we got 16,056,320 geese. All right, how many is that? 1, 2, 3, 4, 5, 6, 7. That's 8 years. We got to do a 9th year here. So I got to multiply that by 4 one last time. And this will tell me how many geese I have after 9 years. So this looks like it's 64,225,280. I'll label it in geese. Or is it geesin? I don't know. There you go. Bam. Unfortunately, I kind of did some extra work there because it didn't ask for us to actually figure out how many geese there are. It's okay, because you're going to have to do that on the assignment, all right? What it asked for was the expression for this one. So I know all I did is I took 245 and I multiplied it by 4, but then I kept multiplying by 4, right? I did it 9 times, so 1, 2, 3, 4, 5, 6, 7, 8, and then 9 times, right? And if you were to put this in the calculator, you'd get the 64,225,280 geese as well. Let's simplify this though. All right, we got 245 to start with, and then I took that 245 and I multiplied it by 4 many times. How many times? 1, 2, 3, 4, 5, 6, 7, 8, 9 times. That's what it told us to do in the beginning. So it ends up being 4 to the power of 9. This is the expression they want. And again, if you put this in the calculator, 245 times 4 to the power of 9, you do get 64,225,280 geese. And we were expecting this to be an exponential equation because going back to the beginning here, it was multiplied by 4, right? And that tells us right there that this is an exponential situation. I spelled that wrong, but I don't care. And so we have our exponential expression, which takes on the form a times b, the base, to the power of x. We just happen to know all three of these values to solve it, right? So a, that's always going to be your starting value. B is the number that you're repeatedly multiplying by that starting value, and x tells you how many times you're going to do it. So both of these examples that we just did, they told us how many times we're going to repeatedly multiply these, but in some of the other problems they're not going to, in which case they probably will want some kind of equation instead of an expression. Again, an expression does not have an equal sign, an equation does. The game allows you to double your score every time you score a bullseye. Your current score is 8. If you only scored with bullseyes, write an equation that will calculate your score in relation to how many bullseyes you hit. Let S stand for your score and B stand for number of bullseyes you hit. Okay, so on this one, so I'm going to skip all the repeated multiplication on this one, especially since we don't know how many times you're going to hit the bullseye. But what I see is that your current score is 8. That tells us that you're going to start with the score of 8. All right, so in my format, A times the base to the power of x, well, I just found my starting value. And that is a score of 8. Then it says, from this score of 8, if you hit bullseyes, right, it says up here, I guess, a game allows you to double your score every time you score a bullseye. So if I were to hit a bullseye, it would double my score. Double means to multiply by 2. Okay, so if I did this once, I'd have 8 times 2 if I hit one bullseye. Now it says you're just going to continually hit bullseyes. It just didn't say how many, right? It said let B stand for number of bullseyes that you hit. We don't actually know how many that is, but it said to use B there, so it would be 2 to the power of B. Meaning if you were to hit it twice, then you'd have 2 to the power of 2. If you were to hit it once even, it would be 2 to the power of 1. Let's say you didn't hit it. Well, then you'd have 0 bullseyes. You'd have 8 times 2 to the power of 0. And that would give you another score of 8. Okay, but this, did they ask? Oh, yeah, they wanted the equation. So it said let S stand. So your score is going to be 8 times 2 to the power of B, because we don't know how many times you're going to hit that bullseye. That's our equation. Cameron is designing a calendar as a fundraising project for math class. The cost of printing is $1,230 plus $1.75 per calendar. Write an equation that models the total cost of printing the calendars, where X equals the number of calendars. You guys take a minute and try this one out too, and we'll go over it. So for this one, okay, those last few examples we saw repeated multiplication. But for this one, we have the cost of printing, and then it's plus this $175 per calendar. So that means you're just adding this $1.75. You could say repeatedly if you want to, but depends on how many calendars you're going to buy. All right, so since we're adding or repeatedly adding, this one is going to be a linear situation. So if you didn't notice that when you're writing your equation, that's okay. But it's not multiplying by 175 every calendar. You're just adding 175 for every calendar, which means we're back to a linear situation. So if I was looking at this equation, I'd look at the cost. That's all you see for my cost. Okay, so what are some of the costs that we have? Well, it says you got the cost of printing. That's how much I guess we'll start with. So you got the printing cost. And again, that for us would be a starting value. Thank you, just set it down. So it says right there, it's $1,230. So you're gonna start with this amount no matter what. If you go to them and say you wanted this calendar printed, but then say you don't want any calendars printed, they're still gonna charge you $1,230 for the printing. But then they say it's gonna be $175 per calendar. So in addition to that, I've got to add how much I'm going to pay for the calendars. Now, if I only purchase one, right? Well, even if I purchase zero, I wouldn't need to add anything. If I purchased one, it'd be 175. If I purchase two, it'd be an additional 175. If I purchase three, it'd be three of these 175s. Four would be 4 times 175. And so we see that we're just multiplying by however many calendars we want. We don't know how many there are. It just said right here, use X for the number of calendars, because we don't know how many we're going to need. But if I just wanted the cost of the calendars, you take 175 for every calendar and then times it by number of calendars. And this is the equation we're looking for. Of course, you could just write it in slope-intercept form, which is what we've been doing. That'd be C equals 175x, right, with a slope of 175, and then plus the 1,230 bucks. Either one of these work. A new town is growing rapidly. Its population triples every year. How large will it be in 6 years if it currently has 250 people in it? So on this one, we see that it's going to triple. Okay, so it's repeatedly being multiplied. This is multiplied by 3. And since it's being repeatedly multiplied, we know that it has to be a exponential situation. Now again, you could say you're gonna take the 250, right? 250, and you're gonna triple that. So on my calculator, do 250 times 3, enter, and that says that after the first year you'd have 750. What is this, population for a town? Well, then multiply that by 3, and this would be 2 years, right? 2250. What do we got to do this for 6 years? So after another year, so times by 3 tells us that after 3 years you have 6,750 people, but after another year it triples again. So that would be 20,250. It triples again. This is the 5th year. That's 60,750 people. But again, it triples. This would be the 6th year here. So times by 3, and you'd have 182,250. I'll just put people. Now that should be my answer. That's what I was asking for. How large will it be in 6 years if it currently has 250 people in it? Well, we just figured that out. You could have just started with an expression though, right? So since we know it was an exponential equation because it's tripling every year, we're looking for something like this. So again, the A is our starting value. And it said that it currently has 250 people in it. That tells us how much it's going to start with. So we're starting with 250 people. And then you can see here, we just multiplied by 3 over and over and over, 6 times in fact. So you can say, well, times by 3, times 3, times 3, times 3, times 3, times 3. And you can simplify this as to 250 times 3. And then how many times was the 3 multiplied? 1, 2, 3, 4, 5, 6. So if you were to type this in the calculator, 250 times 3 to the power of 6, enter. As it turns out, you get the same exact value of 182,250 people. We already have it written, so I'm not going to worry about labeling it again, but does it matter which way you do this? It doesn't. Some students prefer to just show this repeated multiplication like this. Some students like to show this repeated multiplication like this. We would like you to get in the habit of showing it like this because this is the way we're going to start looking at these equations, especially when we start to graph them. But it's if you can understand that you can write it like this in the beginning, you're probably a step ahead because most of this stuff is pretty new to us. Let's say we wanted to type this in the calculator, okay? So just the 250 times 3 to the power of 6. So you type in 250, and then you type in the multiply, which is just x, right? Multiply. And then you type in 3. Now to get the exponent on this one, you got to go one button above division. It looks like this. It's called a caret. You can call it an arrow if you want. I don't care, but it's the exponent button, all right? And then you type in 6, and then just push enter. Once you do, in the calculator, it will tell you it's 182,250 people. Don't forget to label these answers because it is a word problem, right? A certain strain of virus multiplies by 5 each day. If it starts with one virus, calculate how many viruses there would be in 2 weeks. Now you can show the repeated multiplication on these. I'm not going to. I'm going to use I'm going to write the equation, then I'm going to do it. Okay, so remember, I do see that I'm looking at, it multiplies by 5 each day. So we're repeatedly multiplying by 5, but that's every day. But since it's repeated multiplication, I am expecting an exponential situation. So it's A times B to the power of X. And it did say to calculate how many viruses this will be. Let's find out. Okay, so right off the bat, it says a certain strain of virus. It starts with one virus. Okay, so that's my starting value. A is my starting value. Right now, it says there's one virus. But it's going to multiply by 5 each day. So since I'm multiplying by 5 each day, that's my B value. So I'm multiplying by 5. And it says it's going to happen for 2 weeks. Now, a mistake that's made here is where students say, well, it's in 2 weeks, so it's 5 to the power of 2. Remember, it's multiplying by 5 every day, not every week. So what we need to figure out is how many days are in 2 weeks. Well, there's 7 days in 1 week. So this goes back to multiplication. Since there's 7 days in 1 week, but you have 2 weeks, you have 7 groups of 2. 7 times 2 is 14. So it's not to the power of 2. It's actually to the power of 14 because there's going to be 14 days. And you can see right here why I wouldn't want to show the repeated multiplication. I want to show multiply by 5 14 times. You can. I'm just not going to. So I got 1 times 5 to the power of 14 in my calculator. Oh, crap. This is what it shows me. 6103 515 625. And what is that? 6,103,515,625. A certain strain of virus. I'm just going to put virus. I don't think it's viruses because it's not like it's a different virus. It's just one virus. The virus. Viruses? I don't know. I'm just going to keep it like that. That's after 14 days. So that's if it's multiplying by 5. Okay, but again, I use this equation. Some of you may have just said, well, I can start with 1 times 5 times 5 times 5. You do that 14 times, you're going to get the same exact value. You've seen this slide before. We're not looking at graphs right now, but they're going to give us word problems again, and they just want us to be able to tell if we're looking at something linear or exponential. So we're not so worried about the equations or the graphs on this one. What we're concerned about is the changes. Are you changing by addition or subtraction repeatedly? Because if that's the case, then it's linear. If we're actually multiplying over and over and over, then we're looking at something that's multiplication or exponential, which is multiplication. Okay, it's repeated multiplication. And yeah, we know the graphs would look like a straight line if it's linear, and then it's curved if it's exponential. We don't really care about that. All we're concerned about right now is if you add and subtract, then you're looking at linear, multiply, divide, exponential. So for this one, determine whether the scenario can be modeled by a linear or exponential equation. It doesn't ask for the equation. We just want to know if it's linear or exponential. So it says the attendance at a basketball game reduces by 1/3 every 10 minutes during the fourth quarter. Okay, so every 10 minutes, it's going to reduce. It's going to reduce by 1/3. So this means that you're going to multiply by 1/3 every 10 minutes. Okay, so this one's repeated multiplication, which means that we are looking at something that is exponential. Okay, now how do we know it's not linear? Well, it didn't say that it was subtracting 1/3, right? Because it says reduce. Since it's reducing by a fraction, it has to be multiplied by that fraction. If it was reducing by a specific amount, since we're looking at attendance, that's people, you can't have thirds of people, okay? So it has to be reducing by 1/3, multiplying the population by 1/3, which may happen repeatedly every 10 minutes. That's exponential. For this one, the price of soda increases by 42 cents every week. What that means is that right here, we're going to add 42 cents every week. So in other words, you just keep repeatedly adding 42 cents every week. Well, that makes this one linear. Okay, so again, the difference is this one is increasing. Again, they gave us a specific amount. It didn't say that it's multiplying by 0.42. It didn't say it's dividing, it's just increasing 42 cents every week. So you're just repeatedly adding 42 cents all the time. And that's what makes it linear.